Welcome back to Dreamcatcher. Today we are going to read a beautiful chapter, a very important chapter, Alternating Current. We are going to read NCRT text. Oh, are you going to read NCRT text? Don't think like this in your mind. Just relax and feel it. Chapter 7 Alternating Current. Introduction. We have so far considered direct current sources and circuit with DC source. Okay, we have so considered direct source and circuit with DC source. These current do not change direction with time, but voltages and current that vary with time are very common. The electric main supply in your homes and offices is a voltage that varies like a sine function with time. Such a voltage is called alternating voltage or AC voltage, and the current driven by it in a circuit is called alternating current or AC current. Today, most of the electrical devices we use require AC voltage. This is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage over DC voltage is that AC voltage can be easily and efficiently converted from one voltage to the other by the means of transformer. Okay, the main reason for preferring the use of AC voltage over DC voltage is that AC voltage can be easily and efficiently converted from one voltage to the other by the means of transformers. Further, electrical energy can also be transmitted economically over long distance. AC circuit exhibit characteristics which are exploited in many devices of daily use. For example, whenever we tune our radio to a favorite station, we are taking advantage of a special property of AC circuit. One of many that you will study in this chapter. Okay. The phases AC voltage and AC current are contradictory and redundant respectively, since they mainly mean literally alternating current voltage and alternating current. Still, the abbreviation AC to designate an electrical quantity displaying simple harmonic time dependence has become so universally accepted that we follow others in its use. Further, voltage, another phase commonly used, means potential difference between 2 points. Voltage means the potential difference between 2 points. The next page. Nikola Tesla, who was born in 1836 and passed away in 1943. He was a scientist, Yugoslav scientist, inventor, and a genius. He conceived the idea of rotating magnetic field, which is the base of the practically all alternating current machinery, and which helped usher in the age of electric power. He also invented many other things: the induction motor, the polyphase system of AC power, and the high frequency induction coil. Is used in radio and television sets and other electronic equipments. The SI unit of magnetic field is named in his honor. The AC voltage applied to a resistor. A resistor connected to a source of AC voltage. The symbol for an AC source in a circuit diagram is given. Okay. Then we consider a source which produces sinusoidally varying potential difference across its terminal. Let this potential difference, also called AC voltage, be given by V is equal to Vm sin omega t, where Vm is the amplitude of the oscillating potential difference and omega is the angular frequency. Okay. To find the value of current through the resistor, we apply Kirchhoff's loop rule, that is summation Et is equal to 0. Loop rule. Vm sin omega t is equal to IR. I is equal to Vm by R into sin omega t. Since R is a constant, we can write this equation as I is equal to Im sin omega t, where the current amplitude Im is given by Im is equal to Vm by R. Equation is just Ohm's law, which four resistors work equally well for both AC and DC voltage. The voltage across a pure resistor and the current through it, given by the equations on 7.1 and 7.2 in the textbook, are plotted as a function of time in figure 7.2. Note in particular that both V and I reach 0 minimum, maximum values at the same time. Clearly, the voltage and current are in the same phase with each other. We see that, like the applied voltage, the current varies sinusoidally and has corresponding positive and negative charges during each cycle. Thus, the sum of the instantaneous current value over one complete cycle is equal to 0. And the average current is 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electric charge. As you know, joules heating is given by I square R and depends on I square, which is always positive, whether I is positive or negative. There is joule heating and dissipation of electrical charge when a current passes through a resistor. The instantaneous power dissipated in a resistor is P is equal to I square, R is equal to I square M, R sin omega t. Then, the average value of P over a cycle is given when the bar over the letter denote its average value and another symbol given here, that is the less than and greater than symbol, denote the average of the quantity inside the bracket. Since I square M and R are constant, we can take them outside. So, sin square omega t. Using the trigonometric identity, sin square omega t is equal to 1 by 2 into 1 minus cos omega t. We have sin square omega t is equal to 1 by 2 into 1 minus cos 2 omega t. cos sin square omega t is equal to 1 by 2. To express AC power in the same form as DC power, a special value of current is defined as used. It is called root mean square or effective current. Okay. AC power to form as same as DC power. Okay. The peak current Im by I is equal to Im by root 2 is equal to 0.7 m. You know, okay. The next page. The RMS current I is related to the peak current Im. Then okay, it's just learn that V is equal to Vm divided by root 2 is equal to 0.702, where Vm is equal to Im into R, because V is equal to IR. So V can be written as Vm and I can be written as Im into R. So Im can be written as Im by root 2 and V can be written as Vm by root 2. So Vm by root 2 is equal to Im. Vm divided by root 2 is equal to Im divided by root 2 into R. The equation gives the relationship between the AC current and AC voltage and is similar to that in the DC case. This shows the advantage of introducing the concept of RMS value. In terms of RMS value, the equation for power and the relation between current and voltage in an AC circuit are essentially the same as those of DC case. Okay, just underline those. Then, it is customary to measure and specify RMS value for AC quantities. For example, the household line voltage of 220V in an RMS value with a peak voltage Vm is equal to root 2V. That is 1.414 into 220 is equal to 311. Okay, example. In fact, that the I or RMS current is equivalent to DC current that would produce the same average power loss as the alternating current. P is equal to V square by R, which is equal to IV. Since V is equal to IR, we can write like that. Okay, next is 7.3, that is representation of AC current and voltage in rotating vectors. In the previous section, we learned that the current through a resistor in the phase with AC voltage. So representation of AC current and voltage by rotating vectors, that is the phasors. In the previous section, we learned that the current through a resistor in a phase with the AC voltage. But this is not in case of an inductor, a capacitor, or a combination of these circuit elements. In order to show the phase relationship between the voltage and the current in an AC circuit, we use the notion of phasor. The analysis of an AC circuit is facilitated by the use of an Phasor diagram. A phasor is a vector which rotates about the origin with the angular speed omega as shown in the figure 7.4. The vertical component of phasor V and I represent the sinusoidally varying quantities V and I. The magnitude of phasor V and I represent the amplitude or the peak value of Vm and Im. Okay. The projection of the voltage and the current phasor on vertical axis, Vm sin omega t and Im sin omega t respectively represent the value of voltage and current in that instant. And as they rotate with frequency omega, the curves in figure 7.4b are generated. Okay. Then from figure 7.4a, we see that the phasor V and I are for case of resistor are in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is 0. Then the AC voltage applied to an inductor. The figure 7.5 shows that AC source are connected to an inductor. Usually, inductors have appreciable resistance in their winding, but we shall assume that this inductor are negligible resistance. Thus, the circuit is purely inductive AC circuit. Let the voltage across the source V is equal to Vm sin omega t. Using the Kirchhoff's loop rule, summation Et is equal to 0. Since there is no resistor in a circuit, V minus L into di by dt is equal to 0. Where the second term is the self-induced Faraday EMF in the inductor and L is the self-inductance of the inductor. The negative sign shows from Lenz's law. Di by dt is equal to V by L, that is equal to Vm sin omega t by L. The equation 7.11 implies that the equation for IT, the current as the function of time, must be such that the slope di by dt is a sinusoidally varying quantity with the same phase as the source voltage and the amplitude given by Vm by L. To obtain the current, they integrate dy by dt with respect to time. So di by dt into dt is equal to Vm by L sin omega t. And we get, after integrating, we will get I is equal to minus Vm by omega into L cos omega t plus a constant. We can call it as C. Constant is C. The integration constant has the dimension of current and is time independent. Since the source has an EMF which oscillates symmetrically about 0, the current it sustains also oscillates symmetrically about 0, so that no constant or time independent component of current exists. Therefore, the integration constant is 0. So minus cos omega t is equal to sin omega t minus pi by 2. We have I is equal to Im into sin omega t minus pi by 2. Where Im is equal to Vm by omega L is the amplitude of the current. The quantity omega L is an analogous to resistor and is called inductive reactance, denoted by XL, which means the XL is equal to omega L. The amplitude of the current Im is equal to Vm divided by XL. The dimension of inductive reactance is same as that of the resistance and the SI unit is ohm. The inductive reactance limits the current in purely inductive circuit in the same way as resistance limit the current in a purely resistive circuit. Okay. The inductive reactance is directly proportional to inductance and to the frequency of the current. The comparison of the equation 7.1 and 7.12 for the source voltage and the current in an inductor show that the current lags the voltage by 90 degree or 1/4 cycle. It shows that the voltage and the current phasors in the circuit phase in the present case at instant t1. The current phasor I is pi by 2 behind the voltage phasor V. When rotated with frequency omega counterclockwise, they generate the voltage and circuit and current given by the equation 7.1 and 7.12. We see that the current reaches its maximum value later than the voltage by 1/4 of the period. So T by 4 is equal to pi by 2 by omega. You have seen that an inductor has reactance that limit current similar to resistance is DC circuit. So P is equal to IV Im sin omega t minus pi by 2 into V0 sin omega t. So is equal to minus Im Vm cos omega t into sin omega t. Okay. The average power over a complete cycle is PL is equal to minus Im Vm by 2 into sin 2 omega t is equal to 0. Since the average of sin omega t over a complete cycle is 0. Here the average power supplied to an inductor over one complete cycle is 0. So yeah, then figure, we'll tell that figure 240 later, figure the page number 240. Next is AC voltage applied to a capacitor. The figure 7.8 shows an AC source then generating AC voltage V is equal to V0 sin omega t connected to a capacitor only. A purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow from the short point required to charge the capacitor. As capacitor accumulates on the capacitor plate, the voltage across them increases, opposing the current. That is, the capacitor in a DC circuit will limit or oppose the current as it charges. When a capacitor is fully charged, the current in the circuit falls to 0. And you know, the capacitor is alternatively charged and discharged as the current reverses each half cycle. V is equal to, we know Q is equal to CV. From that, V is equal to Q by C. V is equal to sin 0. Normally in text we use sin Vm, but V0 sin omega t can be written. V0 sin omega t is equal to Q by C. So I is equal to dQ by dt. and Q can be written as I is equal to d by dt into Vm into C sin omega t. Then omega CV0 cos omega t. Simply cos omega t is equal to sin omega t plus 90, and which can be written as I is equal to I0 sin omega t plus 90. Okay. Here the amplitude of the oscillating current is Im is equal to omega CVm, and we can rewrite it as Im is equal to Vm divided by 1 by C omega, and 1 by C omega plays a role of resistance, and it is called capacitive resistance, and it is denoted by Xc. Earlier in the earlier we said that the capacitor in a DC circuit will limit or oppose the current as it charges. Okay, voltage opposing the current. Here omega c. Okay, so leave it. Xc is equal to 1 by omega c, that is Im is equal to Vm divided by Xc, or I0 is equal to V0 by Xc. The dimension of capacitive reactance is same as resistance, and the SI unit is ohmmeter. The capacitive reactance limit the amplitude of the current in a purely capacitive circuit in the same way as resistance limit the current in a purely resistive circuit, but it is inversely proportional to frequency and capacitance. A comparison in figure 7.16 with the equation the source voltage 7.1 shows that the current is 90 degree ahead of voltage. Here the current phasor I is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. The current reaches its maximum value earlier than the voltage by 1/4 of the period. And the instantaneous power supplied to a capacitor Pc is equal to I0 V0 by 2 into sin 2 omega t. In case of an inductor, the average power Pc is equal to 0. It's over a complete cycle. It is explained in detail in figure 7.10. Okay, the current lags the voltage by pi by 2 in case of a capacitor, and the current leads the voltage by pi by 2. Pi by 2. Okay. The next is AC voltage applied to a series of LCR circuit. The figure 7.12 shows that the series of LCR circuit connected in an AC circuit epsilon as epsilon 0. Okay, I'm a little confused. Q is the change on the capacitor, and I is the current, and time t we have to find the Kirchhoff's loop rule. L into di by dt plus IR plus Q by C is equal to V. We want to determine the instantaneous current I and its phase relationship to the applied alternating voltage. Okay, the Phasor diagram solution. Here the AC current in each element is same at any time, having the same amplitude and phase. I is equal to I0 sin omega t plus 90. Let I be the phasor representing the current in the circuit, and let VL, VR, VC and V represent the voltage across the inductor, resistor, capacitor and the source. Then okay, you know, VRMS is equal to IM into R. Just leave it. VL plus VR plus VC is equal to V. And the phasor relation whose vertical component gives the above equation is VL plus VR plus VC is equal to V. Since VC and VL are always along the same line and in the opposite direction, they can be combined to a single phasor VC plus VL and has a magnitude VCM minus VLM, since V is represented as the hypotenuse of a right angle whose sides are VR and VC plus VL, and the Pythagorean theorem gives V0 V square is equal to V RMS square plus you know, better we put X L X C and all. Okay, so Im is equal to Vm divided by root of R square plus Xc minus XL the whole square, and IRMS is equal to VRMS divided by XZ. Z is equal to root of X square plus Xc minus XL the whole square. Okay. Since the phasor I is always parallel to the phasor VR and the phase angle phi is angle between VR and VL can be determined from tan theta is equal tan phi is equal to Xc minus XL divided by, you see that VRMS. So tan phi is equal to Xc minus XL divided by R. Here the impedance diagram, which is a right triangle with Z as hypotenuse. Then if Xc is greater than XL, phi is positive and the circuit is predominantly capacitive. If XL is greater than Xc, then phi is negative and the circuit is predominantly inductive. Consequently, the current in a circuit lacks the source voltage. Since we have obtained the amplitude, phase of the current for an LCR circuit using the technique of a phasor, but this method of analyzing AC circuits suffers certain disadvantages. First, the phasor diagram say nothing about the initial condition. One can take any arbitrary value of t and draw different phasors which shows the relative angle between different phasors. The solution so obtained is called a steady state solution. This is not a general solution. Additionally, we do have a transient solution which exists even for V is equal to V is equal to 0. Then the general solution is the sum of transient solution and the steady state solution. Then comes analytical solution. Since we have learned this much today, I am planning to continue this session by giving you the rest of the topic as a homework. So I wanted you to read the rest of the textbook by yourself and then comment on the comment box. Thank you.